All right, let's talk about one of the most critical topics in Java, synchronization. Seriously, if you're building any kind of multi-threaded app, or you're gearing up for a technical interview, you have to get this right. It's all about making your code work correctly when multiple things are happening at once. So let's just dive right in.
So I want to start with a question that seems almost too simple. You look at count++. It's one line. It's basic. What could possibly go wrong with that? Well, it turns out that in a multi-threaded world, that one innocent-looking line is a ticking time bomb. But why?
Okay, so before we can talk about the solution, we have to get a really clear picture of the problem. We're going to look at something called a race condition, and we'll see how a super simple counter can just completely fall apart.
Check out this counter class. It couldn't be simpler, right? Now imagine two threads. Let's call them thread A and thread B, both trying to call increment at pretty much the same time. Let's say the count is at 5. Thread A reads the value 5. But hold on. Before it can add 1 and save it, the CPU scheduler pauses it and switches over to thread B. Now thread B comes in, and what value does it read? It also reads 5. So thread B adds 1, writes 6 back. Then thread A wakes up, remembers it had a 5, adds 1, and it also writes 6. We called increment twice, but our count only went up by 1. Poof! An entire operation just vanished into thin air. That, right there, is a race condition.
So that's the chaos. How do we fix it? How do we stop our threads from stepping all over each other and corrupting our data? Well, the answer in Java is synchronization. This is the tool we're given to bring order back from the chaos and make our code what we call thread safe. All right, if you're in an interview, this is the definition you want to have in your back pocket. Think of synchronization as a traffic cop for your code. It stands in front of a shared resource, like our count variable, and only lets one thread in at a time. The whole point? To make sure our data stays consistent and predictable. But why do we even need a traffic cop? Well, it's because all of our threads are basically playing in the same sandbox, the heap memory. And that little count++ operation, it's not one single action. The CPU sees it as 3 steps. First, read the current value. Second, add 1 to it. And third, write the new value back. The CPU can hit pause between any of those steps, letting another thread jump in and cause mayhem. And the result is always the same: messed up data and a program in a corrupted state. Now here's a killer line for an interview. Synchronization gives you 2 big promises. The first is mutual exclusion. That's our traffic cop, right? Only one thread gets access at a time, mutually exclusive. But the second one, visibility, is just as important. It guarantees that when one thread makes a change inside a synchronized block, other threads will actually see that change right away. No stale data. So this brings us to a key concept, the critical section. This is the specific chunk of your code that's actually touching the shared data. Your job as a developer isn't just to slap synchronized on everything. It's to be a surgeon. You need to identify the absolute smallest, most precise block of code that needs protection. That's how you keep things safe without killing your performance. Okay, so we get the what and the why. Now let's get into the how. Java doesn't just give us one tool. It gives us a few different ways to implement synchronization. And, choosing the right one is absolutely essential for getting that balance between safety and speed. You've basically got 3 main options in your toolkit. You can synchronize an entire method. You can just synchronize a specific block of code inside a method, which, spoiler alert, is usually the better choice. Or you can use something called static synchronization for static data. Let's see how they compare. This table kind of says it all, doesn't it? Synchronizing a whole method is easy, sure, but it's like using a sledgehammer to hang a picture frame. You lock the entire method from start to finish, even the parts that don't need locking. A synchronized block, on the other hand, gives you that surgical precision. You wrap only the critical lines of code, which leaves the rest of the method free for other threads, and that means way better performance and a lot more flexibility. So this is the golden rule. Seriously, burn this into your brain. The mark of a great concurrent programmer is making your critical sections as small and as fast as humanly possible. This is exactly why synchronized blocks are almost always the way to go. It shows you understand that trade-off between keeping things safe and keeping things fast. Okay, but when we say we lock something, what are we actually locking? Well, there are 2 fundamental types of locks. There's an object lock, which is tied to a specific instance of an object. Think this. You use that to protect instance variables. But what if your data is static, meaning it's shared across all instances of a class? For that, you need a class-level lock. If you use the wrong one, guess what? You've got 0 protection. So we've been throwing this word lock around a lot. But what is it really? Let's pull back the curtain for a second and look at the magic that makes this all possible. It's called the intrinsic lock. This is honestly such a cool concept. Every single object you create in Java comes with its own secret built-in lock. It's sometimes called a monitor lock. It's just there, waiting. And the synchronized keyword is basically the magic command that tells a thread, hey, go grab that object's built-in lock before you proceed. And when the thread leaves the synchronized section, it automatically releases the lock for the next thread in line.
Okay, quick pop quiz to see if you're following. Let's say thread A gets a lock on counter object 1, and thread B gets a lock on a totally separate counter object 2. What happens then? Do they block each other?
The answer is a big no, and this is so important to understand. They don't block each other at all. Think about it. They're like two people with two different keys trying to get into two different houses. There's no conflict. Each thread has the lock for its own specific object instance. This just proves that the lock is tied to the object, not the class as a whole.
Okay, you've got the fundamentals down solid. Now let's talk about where people tend to get tripped up. These are the tricky questions and common mistakes that you're almost guaranteed to see in a technical interview about concurrency.
And here it is, the absolute classic Java interview question. You're sitting across from the hiring manager, they lean forward, and they ask you, can you put the synchronized keyword on a constructor? What do you say?
The answer is a simple, confident, and emphatic no.
And here's the simple reason why. Synchronization needs a lock, right? And a lock belongs to an object. But what's the whole point of a constructor? Its job is to create the object in the first place. The object literally doesn't exist yet when the constructor is running, so there is nothing to lock. It's a logical impossibility. If you need to control the creation of objects safely, you use other patterns, like a synchronized static factory method.
And beyond the constructor trap, there are a few others to watch out for. The biggest one is just being lazy and synchronizing huge chunks of code, which just kills your performance. Other classic mistakes include grabbing the wrong lock, like using an instance lock for static data, or just blindly using synchronized this everywhere without actually thinking if this is the correct object to be locking on. And that really brings us to the core idea, the big takeaway from all of this. Synchronization is a trade-off, plain and simple. You are trading some of your application's concurrency, its ability to do things in parallel, in exchange for a guarantee of correctness. A good engineer knows how to use synchronized. A great engineer knows how to design their code to need as little of it as possible by keeping those critical sections tiny. So we'll end on this thought. You now have the tools and you understand the principles behind writing correct, thread-safe Java code. But the real art, the real challenge is in the application. So the question I'll leave you with is this. In your next project, how are you going to strike that perfect balance between safety